November 2019, paper 4, variant 3. Question 1. Figure 1.1 is the top view of a tank in an aquarium. The tank is filled with salt water. The depth of the water is 2 meters. Calculate the volume of the water in the tank. Okay, we need to find the volume, which would be the length times width times the height. If it were a regular rectangle, we need to divide it into two rectangles. How can I divide it into two rectangles? If I draw a line in the middle, so this would be a rectangle 1.6 times 1.1. And this would be a rectangle 1 times 1.1 times 3.2. So 1.6 times 1.1 plus 3.2 times 1. This would give you a total area of 4.96. This is the total area. But then you need to multiply it by the depth, okay, to find the volume. So the volume would be the area times the depth, or the area times the height. 4.96 times the depth, which is 2, multiplied by 2. This would give you a total volume of 9.92 meters cubed. 9.92 meters cubed. Okay? The density of the water is 1.1 times 10 to the power of 3 kilograms per meter cubed. Calculate the mass of the water in the tank. Density equals mass over volume. So to find the mass, we need to say density times volume. The density is 1.1 times 10 to the power of 3 times the volume, which is 9.92, multiplied by 1.1 times 10 to the power of 3, which would give you a total mass of 10,912, which is 10,900 kilograms. Okay. Calculate the pressure due to the water at a level of 0.8 meters above the base of the tank. Again, read it carefully. Calculate the pressure due to the water at a level of 0.8 above the base of the tank. So pressure equals rho gh. Okay, pressure equals rho gh. Is the height 0.8? No, it's not 0.8. And that's the trick of this question. Okay, he wouldn't give you 3 marks that easily. He has to trick you. It's the depth isn't 0.8, it's 0.8 above the base of the tank. So if you look at the tank, okay, the total depth of this tank was what was 2 meters. He said 0.8 meters above the base of the tank, 0.8 meters. So actually, the depth was what? The depth was 1.2. The depth was 1.2. 2 minus 0.8. So 2 minus 0.8 would give you a depth of 1.2. Pressure equals rho gh. 1.1 times 10 to the power of 3 times g 9.8 times the height 1.2. 1.1 times 10 to the power of 3 times 9.8 times 1.2, which is 12,936. You can write it down as 13,000 pascals. 13,000 pascals. Okay? Okay. State in words the equation that defines the moment of a force. Moment of a force. How can I find the moment? Moment equals force times perpendicular distance. That's it. Moment equals force times perpendicular. Okay. Distance. It's okay if you write down perpendicular wrong, or if the spelling is incorrect. Again, this is a physics test. It's not an English test. It's okay if you have some silly spelling mistakes. State what is meant by the moment of the force. A moment of a force is the yes, it is the turning effect. Moment is the turning effect. Turning effect of this force. Force is a vector quantity. Explain what is meant by a vector quantity. A vector quantity is a quantity that has a magnitude and a direction. It has to have a magnitude and a direction. Figure 2.1 shows a tower crane used to lift a load on a construction site. Explain how the counterweight prevents the crane from toppling over. How does this counterweight prevent the crane from toppling over to the right or to the left or whatever? It yes, it creates a moment. What type of moment? That's the question. It creates an anti-clockwise moment. So, therefore, the anti-clockwise moment would be equal to the clockwise moment. So it creates an anti-clockwise moment. Hmm, Anti-clockwise moment, which would be equal to the which would be equal to the clockwise moment. Yeah, clockwise moment of the load. The load will exert or will create a clockwise moment in the opposite direction. Hmm. Figure 3.1 shows a waterfall. Describe the main energy transfer, which is taking place as the water falls. As it's falling down, the main energy transfer is from gravitational to kinetic. Yes, from gravitational potential energy to kinetic energy. The speed of the water as it hits the bottom is 21 meters per second. Calculate the height of the water. Can I find the height of the water? Yes, we would equate gravitational potential energy to the gravitational potential energy equals kinetic energy. So basically mgh equals half mv squared. Remove the masses. So gh equals half v squared. To find the height would be equal to v squared over 2g. 21 squared over 2 times 9.8. What is 21 squared over 2 times 9.8? 22.5 meters. 22.5 meters. One State and explain any assumption you have made. What is the main assumption that we have made in this question? Main assumption in any question that has energy is what? The main assumption is that no energy is lost to the surroundings. No energy is lost to, okay, the surroundings. The sun is the source of energy for most okay energy resources used to provide electricity. State two energy resources that have another source for their energy. Okay, nuclear, tidal, geothermal. Yes, exactly. Okay, nuclear fission, tidal, and geothermal. Excellent. Okay. Hmm. Solids have a fixed shape. This is a really easy answer. Okay. 6 bonus marks, honestly. Explain in terms of forces, okay, between their molecules, arrangement, why solids and gases have these properties. Okay, let's write them down. So solids have a fixed shape. Liquids adapt to the shape of the container. Gases fill their container. What is the difference between a solid, a liquid, and a gas? Solids have fixed shape. Solids have, okay. Why? Because they have a lattice arrangement. They have a fixed arrangement. Mm, They have a fixed lattice arrangement. What about the forces? Hmm. Very strong forces. Very strong forces between the molecules, or intermolecular forces, if you might say, okay, between the molecules, between the molecules. What about the liquids? Do they have a fixed shape? No, they are not fixed in place. Okay, and weaker forces. Okay, not fixed in place. They actually slide over each other, and we can say they have an irregular arrangement. The distances between them are larger, okay, and they have weaker forces. Okay, weaker forces between the molecules. Hmm. Gases. What about the gases? Well, this is the easiest. What the distances between the molecules are very far apart. Irregular arrangement. Okay, irregular arrangement, very far apart. Okay, and extremely weak forces, or sort of non-existent forces. Okay, very weak forces between the molecules. Okay, moving on. An electric kettle contains water at temperature, okay, 19 degrees, power 3 kilowatts, switched on for 3.5 minutes. Find the electrical energy. So the energy is equal to the power times the time. The power is 3 kilowatts, so 3000 watts, times the time, which is 3.5 minutes. You have to convert the minutes into seconds. So 3000 times 3.5 times 60. 630,000 joules. 630,000 joules, or you can write it as 6.3 times 10 to the power of 5 joules. 6.3 times 10 to the power of 5 joules. At 3.5 minutes, the temperature of the water reaches 100 degrees Celsius. The volume of the water in the kettle is 1,700 centimeters cubed. The density is 1 grams. The specific heat capacity is 4,200 joules per kilogram degree Celsius. Calculate the thermal energy gained by the water. Can I find the thermal energy gain? Okay, E equals mc delta T. Do I have the mass? No, but I can find the mass because I have uh, you have the volume and you have the density. So mass equals density times volume. So basically 1 times 1,700, which is 1,700 grams. You need to convert these grams into kilograms. Divided by 1,000, which is 1.7 kilograms. So E equals mc delta T. 5 marks is a lot. 5 marks is a lot. That's why you need to write down a lot in this question. mc delta T. So 1.7 1.7 times 4,200 times delta T, the change in temperature. Is it 100 degrees Celsius? No. It was initially 19 degrees Celsius and it reached 100 degrees Celsius. So the change in the temperature would be 81 degrees, or 100 minus 19. Let's calculate it. 1.7, this is not 17. 1.7 times 4,200 times 81 would give you 578,000 joules. 578,000 joules. 5.78 times 10 to the power of 5 joules. Can I find the efficiency of the kettle? Okay, that's easy. Efficiency would be equal to the useful output over the total input. Useful output over the total input. Which is which? Which of these numbers is the useful output and which of these numbers is the total input? if you do not know, or if you cannot say which is the output and which is the input, okay, the input, the total input is always the larger number. So basically this number, 6.3, would be the total input and 5.78 would be the total output. So 5.78 times 10 to the power of 5 is the output, and 6.3 times 10 to the power of 5 is the total input. You can multiply by 100 to find the efficiency in percentage. Okay, 5.78 over 6.3. 0.917, or basically 91.7, or 92%. It is 92%, which is very efficient actually. 92% is very efficient. Hmm. Figure 6.1 represents wave fronts. State the name, region A and in region B. Region A is a compression. Region A is a, what about region B? Rarefaction. Hmm. Draw a double-headed arrow to show one wavelength. One wavelength would be the distance between two successive compressions or two successive rarefactions. So the distance between this point and this point. These are two successive compressions. This would be the wavelength. This would be one wavelength. The loudness of the sound is increased at the same pitch. Explain any change that would be in the pattern of the wavefronts shown. Loudness is increased. As you increase the loudness, as you increase the loudness, what happens is that the amplitude increases. Amplitude increases. Does the wavelength change? No, the wavelength doesn't change. The wavelength doesn't change. So we will say that the wavelength remains the same. Wavelength, okay, wavelength remains the same. The amplitude increases, okay, the amplitude increases. And how can we show on this wave, okay, this pattern of the compressions and the rarefactions, how can I show that the amplitude has increased with the same wave length? All you need to think about is that the compressions will be compressed even more, and the rarefactions will have, no, the distance between the molecules in the rarefaction will increase. Basically, the distance between these wavefronts in the rarefaction would increase, and the distance between the wavefronts in the compression will decrease. The compressions will get closer, and the rarefactions will get further apart. Okay, so that's how we can show a higher amplitude if you want to draw it as a longitudinal wave. Okay, so the compressions will increase. Okay, we'll get closer together. We'll get, okay, closer together, or the waves, the wave fronts will get closer together, and the rarefactions, okay, the rarefactions will get further apart. Will get further apart. Hmm. The wave passes into water. State and explain any change in the pattern of the wave fronts shown in 6.1. This is a sound wave, right? This is a sound wave. As the sound wave moves from air to water, what happens? The speed increases. So how can I indicate that the speed increases? The wavelength will increase. Okay, the wavelength will increase, so they are more spread out. Okay, so the speed increases, the wave length increases, the wavelength increases, the waves are more spread out. Let's say that the wave fronts are more spread out. Hmm. Okay, good. Figure 7.1 shows the position of a converging lens, its principal axis, and an object O. Each principal focus is labeled F. On figure 7.1, draw a ray diagram to locate the position of the image formed by the lens. Can I draw the rays? Yes, I can draw the rays. First one, okay, this is quite obvious that the image will be virtual, upright, and enlarged. It will appear behind the object on the left side. So the first line will be drawn parallel, and then it will refract passing through the through the principal focus. The second line will pass directly through the center without being refracted. They won't meet on the other side, therefore you need to extend these lines. Okay, need to extend these lines this way, and they will both meet on this side, somewhere on this side, and this is the image. The image will appear on this side. This is the image, I. This is the image, virtual, upright, and enlarged. So if I want to describe the image, it is virtual, upright, and enlarged. Okay? Good. Images formed by lenses sometimes have colored edges. Okay? Colored edges. Why would they have these colored edges? Hmm. Why would they have these colored edges? Suggest a reason for this. Suggest a reason for this. Huh? Any ideas? Any ideas? Yeah. If you think about it, okay, these colored edges might be formed due to the refraction of light. Light, when light passes through a prism, it might disperse, and different colors will refract at different angles, right? Different angles. So due to the dispersion of light, okay, due to the dispersion of light in the glass, different colors might have different wavelengths due to the dispersion, okay, dispersion of light with different wavelengths, with different wavelengths. That's it. Hmm. Okay. يلا, all good. Hmm. Figure 8.1 shows a negatively charged conducting sphere. On figure 8.1, draw the electric field pattern around the sphere. How can I draw the electric field pattern? It's moving into the sphere. Okay. This is a negative charge, so you have to draw 4 arrows at least moving into the sphere. Okay, 4 arrows moving into the sphere this way. The current in the electrical device is 0.21 amperes. Calculate the charge that flows during a 0.75 second period time. Okay, charge. I equals Q over T, or Q equals IT. Q equals IT. 0.21 times the time, which is 75. This would give you a charge of 21 coulombs. No, I'm sorry, 16 coulombs. 16 coulombs. Yeah. Huh. Figure 9.1 shows a circuit containing an LED, two resistors in parallel, each of resistance R. The normal operating voltage is 2.1 and the normal current is 0.19 amperes. The LED 2.1 and 0.19. Figure the potential difference across the LED is measured with a voltmeter. Draw the symbol for the voltmeter. Okay, this is a bonus mark. Voltmeter. Okay, draw the current. Can I draw the current? the ammeter. Okay, so basically he gave us 2 bonus marks. Calculate the value of R when the LED is operating normally. So when the LED is operating normally, the voltage of the LED is what? Is 2.1 volts. Okay, not bad. What is the voltage? Voltage is 2.1 volts and the current is 0.19 amperes. So the total current um, in the circuit is 0.19 amperes. If the voltage is 2.1 volts on the LED, so the voltage on the resistors is also, it's not also, is 3.7 minus 2.1, which is 1.6 volts. صح 1.6 volts on each of these resistors. On each of these resistors. Can I find the resistance of one resistor? Yes, I can find the resistance of one resistor. R equals V over I. R equals V over I. R equals V over I. So what would the voltage of one of these resistors be? It would be 1.6. It would be 1.6. And the current in each of these resistors would be what? Current in each of these resistors would be 0.19 divided by 2. Why would it be 0.19 divided by 2? Because this is the total current. It would be divided by 2. It would be divided equally. It's not the case for all of the resistors. It is only the case if the resistors are equal. If the resistors are equal, then the current will be divided by 2. So the current in each of these resistors is 0.19 divided by 2. What's 0.19 divided by 2? It would be 0.095. So the current in each of these resistors is 0.095 amperes. So you have the voltage in each of the resistors, you have the current in each of the resistors. Can I find the resistance? Yes. 1.6 divided by 0.095. Using your calculators, you can find the total resistance, which would be 16, okay, 0.8 ohms. 16.8 ohms. Okay, not bad, huh? Yeah. Question 10. Magnet and a coil are attached separately to a door and a door frame as shown in figure 10.1. The purpose of the arrangement is to activate the circuit connected to an LED indicator when the door is opening or closing. So as the door opens or closes, the indicator or this LED will be switched on. Initially the door is closed and then it is opened. Explain why the indicator comes on and then goes off when the door is opened. So initially when the door was closed, it's off. As the door opens up, the light switches on and then off. Okay, the indicator comes on and then goes off when the door is opened. Why does it come on and then go off while the door is open? This is a really nice question. It's quite easy, to be honest. But as the door moves, can you see this magnet attached to the door? It has a magnetic field. It has a magnetic field. As the door moves, what happens? The magnetic field cuts the coil, inducing a inducing a current or inducing a an EMF in the coil. Therefore, so the magnet, okay, magnet cuts, okay, magnet cuts the coil, inducing a current or inducing an EMF, and then so that's why it's on, and then it goes off when then it goes off when the magnet is far away, moves further, moves further. Okay? The door shuts, the indicator comes on more brightly for a shorter time than it did an eye. Suggest and explain why this happens as it shuts more brightly for a shorter time. more brightly, this would mean that it had a larger EMF. صح? It had a larger EMF. Yeah, why? Why would it have a larger? Because the door was being slammed. The door was moving faster. It was moving faster. So you might say that the door was moving faster. The door was moving faster, and the magnet was moving faster. That's the first part of the question. If he's saying more brightly, and then for a shorter time, so the magnet, okay, cut the coil for a shorter amount of time. For a shorter time. Okay? Yeah, we're almost done. A circuit breaker is recommended for use with an electric lawnmower. State two reasons for this recommendation. Why should we have a circuit breaker in a lawnmower? First of all, circuit breakers, what do they do? They protect against what? They protect us against overheating, okay? And they avoid the lawnmower from being damaged, okay? So they protect, okay, protect from, it's like a fuse, from overheating, and they protect the, okay, the lawnmower from being damaged. Okay? Yeah. Last question, question 11. You have three gold nuclei. Three alpha particles are approaching the gold nucleus. We need to see what will happen to these alpha particles. The first one is head-on collision with the nucleus. Hmm. So it will, yes, it will deflect back. Okay, it will deflect back in this direction, for example. Downwards or upwards, doesn't really matter. The second one is coming close to the nucleus. Okay, it's quite close to the nucleus. So it will deflect upwards. Okay, it will deflect upwards. What about the second one? It's coming again close to the nucleus, but it will deflect downwards. It will deflect downwards. Okay, this way. A detector of radioactivity. A detector of radioactivity in a laboratory indicates an average of 16 counts per minute when there is no radioactive samples. So this is the background radiation. A half-life of 1.5 days is placed next to the detector, which indicates a count rate of 208 counts per minute. Calculate the average count rate after 6 days. The count rate that is indicated after 6 days. So you have background radiation of 16. First of all, you need to, yes, you need to subtract. So 208 minus 16. What's 208 minus 16? It is 192. 192. And then 6 days divided by 1.5 days would be 4. 6 divided by 1.5 is 4. So basically we have 4 half lives. We will divide by 4, divide by 2, 4 times. So 192 divided by 2. 192 divided by 2 is what? Is 96. Divide by 2 again is 48. Divide by 2 again, 24. Divide by 2 again is 12. Is this the final answer? No, it's not the final answer because he wants to find the count rate that is indicated. So count rate that is indicated will include the background radiation. So 12 plus 16 will give you a total count rate of 28 counts per minute. Okay. After 6 days. The waste from a nuclear power station includes isotopes of technetium, okay, tin, and selenium. These isotopes are radioactive with half-lives of many thousands of years. State three economic and environmental consequences of producing this waste. So basically, we need to talk about the economic and, uh, which is a really out of the box question. It's not a really physics question. It's more of an economics or a it's not really a physics question. Anyway, what are some problems? What are some of these um, uh, consequences, if you might think about them? Hmm. Some of the consequences might be okay, if I want to store them, would it be that cheap? No, it wouldn't be cheap because you need to find very huge lead or concrete containers and then store them inside these containers and then store them far away. So that would be quite expensive. Okay, very expensive to store. Very expensive to store if you want to store them. Hmm. Type. Will I store them right next to me, for example, in the backyard or whatever? No, definitely not. So you need to transport them to very large distances, very far away, right in the middle of the desert where no one lives, right? So you need to pay a lot to transport these materials. So very expensive transportation. Again, very expensive hmm, to transport. Very expensive to transport. They have to be you have to be stored in very expensive stores or very expensive shielding, lead and concrete shielding. Okay. For example, if I want to talk about an environment problem, an environment consequence, if for any reason there is a spill, okay, if for any reasons there is a spill, then this would cause too much harm to the people. Okay, if it spills, if for any reason, if it spills for any reasons, it would be very dangerous to humans and the environment. And the environment. Okay, okay.